Welcome to Lesson 7E, Superposition of Complex Potentials. In this lesson, I'll discuss two classical examples of superposition, flow around a 2D Rankine half-body and flow around a circular cylinder. I'll also introduce the Alembert's paradox and the boundary layer correction for potential flow. By way of introduction, superposition is where we simply add up two or more potential flows, and since the equations are linear and homogeneous, the result is also a valid potential flow. We already did one example of this, namely a doublet, which is the superposition of a source and a sink, as discussed in a previous lesson. I'll discuss two classical examples of superposition here, the first one being a 2D Rankine half-body. To generate this, we superpose a uniform stream plus a source. In our z-plane, we have the uniform stream with potential function W equal uz, and we have a source at the origin of strength m, so W is equal to m over 2 pi natural log of z. To superpose, we simply add these two up, so W of z equal uz plus m over 2 pi natural log of z. Now let's think about what this will look like. We have flow coming in from the left at speed u, and on the negative x-axis, we have a flow coming out of the source to the left, opposite of u, at infinite speed at the origin, but of course it slows down as we move, and at some location, capital U will be exactly balanced by capital U from the source. These two velocities will cancel out, and this point will have zero velocity. It is a stagnation point. I'll redraw this for clarity. If this is our stagnation point, let's let red streamlines come from the source and blue streamlines come from the uniform stream. So far upstream, the streamlines are just parallel lines that are horizontal. Very close to the source, the streamlines are rays, but since this problem is linear, velocity vectors can be simply added up. So flow that comes out gets swept downstream, something like that. Another one might look like that. Another one might look like that. I'll sketch another streamline, and from the stagnation point, a streamline will look something like that. Meanwhile, on the outside of this last streamline, flow goes around that streamline like this. Of course, it's symmetric from top to bottom, so the streamlines under the x-axis are a mirror image about the x-axis. And now imagine that we have a line source at the origin spewing out red fluid, as shown here, and a free stream coming along with blue fluid. The blue fluid must flow around this set of streamlines, and since streamlines can't cross, all the red fluid stays within this boundary, and all the blue fluid must go around it. This streamline is a special one, which we'll call the dividing streamline, and of course, it's also symmetric about the x-axis. We call it the dividing streamline because it divides fluid that came from the source from fluid that came from the free stream. The red and blue fluids never mix. Let's call this dimension A, the distance from the origin to the stagnation point. By the way, if we treat the dividing streamline as a wall, remembering that we can pick any streamline and pretend it's a wall in potential flow, we have what is called the 2D Rankine half-body. It's a half-body because it never closes on itself. In fact, far enough downstream, it reaches a maximum thickness, and the streamlines eventually become parallel again. But what's inside the body, the red fluid, never crosses over the dividing streamline. In fact, you can even erase all this stuff from the source, and you would just see flow over a body. It's called a half-body because it extends infinitely in the x direction. How do we calculate dimension A? I'll redraw the half-body without the internal flow, so I'll just show some streamlines outside the Rankine half-body. To calculate A, we know that at the stagnation point, which is here, the velocity must be 0, and since W is capital U z plus m over 2 pi natural log of z, then the complex velocity dw dz is simply u plus m over 2 pi z, and we'll set this to 0 at the stagnation point. Well, this equation can be solved easily for z, namely z equal negative m over 2 pi u. which is real, and so it lies along the x-axis, and it's negative, which lies along the left part of the x-axis. In fact, this is how we defined dimension A. Therefore, A is m over 2 pi u. You can analyze this complex potential further to find, for example, the thickness of the half-body, and you can plot its exact shape by plotting the psi equals 0 streamline. And you can do more analysis of this Rankine half-body. Our next example is flow around a circular cylinder. In this case, we superpose a free stream and a doublet. The free stream has speed u, and the doublet has strength mu. So immediately we can write our complex potential as uz plus mu over z. Qualitatively, we're superposing the free stream with the doublet at the origin. Very close to the origin, we have circles as we did previously, but as we keep drawing streamlines, they start to flatten. They're not circles anymore, although they're still tangent to the x-axis. Again, it's symmetric about the x-axis. And just like with the Rankine half-body, there's a point, the stagnation point, where capital U is exactly balanced by speed u in the negative direction, and so the velocity is 0 at the stagnation point. There's a dividing streamline, much like what we had with the Rankine half-body. But in this case, it turns out to be a perfect circle. There are 2 stagnation points, in fact, one in the front and one in the rear. Again, if the flow from the doublet is red and the flow from the free stream is blue, we sketch our streamlines and they look something like this, where just as with the half-body, the red fluid does not mix with the blue fluid, but unlike the half-body, this is a closed body. All the red fluid coming from here is trapped inside this circle. And if we pretend this streamline, the dividing streamline, is a wall, then we get flow around a circular cylinder. Let's call the cylinder radius A. In my undergrad fluids book, I plotted streamlines outside the circular cylinder in non-dimensional form. Here we define normalized x star equal x over a, normalized y is y star, y over a, and psi star, making sure that this is non-dimensional, is psi over ua. With this normalization, we get this plot for any u or mu, and thus any a. This circle will have radius 1 in these non-dimensional coordinates. I just want to mention that both the 2D Rankine body and this circular cylinder flow are two-dimensional. There's no change into the page. Imagine a cylinder of infinite length into the page. But we can have a three-dimensional analogy. If we have a spherical doublet at the origin, we end up with a sphere. And for the Rankine body, if we have a three-dimensional source, we end up with an axisymmetric Rankine half-body. Here's a question. What is radius A in terms of our 2 parameters u and mu? Let's start with the complex potential. W of z is uz plus mu over z. And I'll let the students work this out. Let me know when one of you has an answer.
I could do that one in my sleep, Sonny. A equals square root of mu over u.
That's right, Pops. The math is actually quite simple. We do the same thing we did for the Rankine body, namely, calculate the complex velocity, dw dz, which here is simply u minus mu over z squared. And we set that equal to 0 at the stagnation point, which is right at the front of the body, and there's another one at the back. And this distance is our radius A. We can solve this equation for z, namely z squared equal mu over u, and thus z equal plus or minus the square root of mu over u. And the way we've defined the radius is that at the stagnation points, z equal plus or minus a. A is the square root of mu over u. This is the radius of the circle. So that's our answer. Let's discuss some other properties of this flow. First, let's look at the speed v along the wall being the cylinder. And keep in mind that it's really not a wall at all. It's just a streamline that happens to be a circle. I'll look at the top half only. From the origin to some point along the body, and we'll call this distance s. This is a, and theta is defined from the x-axis. but it's easier to work with this angle, which we'll call gamma. And what we're trying to find is capital V, which is a function of s, s being the distance along the body. Well, some simple math gives us gamma equal pi minus theta. And as I said, V of s is the speed at the surface. Some algebra yields V equal 2u sine theta, which would also be 2u sine gamma from this definition of gamma. S itself is a times gamma. The arc length is the radius times the angle. So combining these, we get V as a function of s is 2u sine s over a. This is the speed along the wall. Sine of 0 is 0, so at the stagnation point, the speed is 0. It reaches a maximum, which is 2u at gamma equal pi over 2 or 90 degrees, where the sine is 1, and then it decelerates to another stagnation point at the trailing edge. So the speed increases, reaches a maximum at the top, and then decreases back to 0. Let's also look at the pressure distribution. For these kinds of flows, we can use the beloved Bernoulli equation. Neglecting gravity, P plus 1/2 rho V squared is equal to a constant. Plugging our speed into this equation, we can calculate the pressure along the wall of the cylinder. Without showing all the math, qualitatively, it turns out that the pressure is highest at the stagnation point and lowest at the top, since speed is 0 at the stagnation point and max at the top. Pressure is everywhere perpendicular to the wall, and it decreases from the stagnation pressure at the stagnation point to its minimum pressure at the top. This pressure field is symmetric from front to back and also from top to bottom. In other words, pressure is symmetric about both the y-axis and the x-axis. Because of the symmetry, there is no lift and there is no drag. The lift we might expect since it's a cylinder, but we know that a cylinder like this will have drag. This leads us to something called D'Alembert's paradox, which states that the drag on any closed two-dimensional body in steady potential flow is 0, not only for a circular cylinder, but for any body shape. Let's take some weird-shaped body like this, for example, that has no symmetry forward and aft or up and down. Potential flow would have some kind of stagnation point at the front and one at the back, and the streamlines would follow the body somewhat like this, and it turns out that the drag is 0. We call it D'Alembert's paradox because we know that this body has to have drag. This result does not agree with physical observation. Why not? Well, in a real flow, we have skin friction drag. Due to viscosity, there will be skin friction along the surface, and we have pressure drag, where the pressure in the front does not balance the pressure in the back. In fact, in a flow like this, you would get massive flow separation from these corners, so the streamlines would look nothing like the ones I had sketched with potential flow. There would probably be some recirculating wake and a net drag, and perhaps some lift in real life due to the non-symmetry top and bottom. So in a real flow, the drag is not 0. Here's another question. Does this, namely D'Alembert's paradox, render potential flow useless? The answer is it depends. Yes, for blunt bodies with flow separation, and no for streamlined bodies without flow separation. I already showed an example of a blunt body. An example of a streamlined body is an airfoil. Again, we have a stagnation point with streamlines that go smoothly along the body, and the flow does not separate anywhere. Later in the course, we'll discuss airfoils like this at angle of attack, and it turns out that you can predict lift as well. And potential flow does a very good job. It turns out that you can also predict drag, namely the skin friction drag, by fitting in a very thin boundary layer. How thin is it, dude? It's so thin that from far away you don't even see it. Therefore, our potential flow is valid along the whole body. And since a boundary layer does have the no-slip condition and friction along the wall, we can predict the drag force. Potential flow gives a 0 drag force, but if we add this boundary layer, we can predict the drag force. And potential flow can do a very good job at both the lift and the drag on an airfoil at angle of attack. But as we'll see later, we have to make sure that the flow leaves smoothly from the trailing edge in order to generate the proper lift. We'll talk about all that in later lessons. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.